For the next maybe 5 or 6 videos, maybe more, I'm not sure, I'm going to be talking about the Laplace transform. So this is going to be a significant part of the calculus playlist I'm making because it's super important in solving differential equations. So if you've been following my playlist, that's kind of the point we're at right now is differential equations. And what a Laplace transform does is it simplifies differential equations so we can solve them much easier in most cases. Okay, so the Laplace transform was created by Pierre-Simon Laplace, and he created it for applications in probability. So if you're in a stats class or a probability class, you're aware of something called the central limit theorem. That's basically why he created it, to solve for the central limit theorem and lots of stuff in probability. So what the Laplace transform does is it takes a function of something from the t domain, which is what we're going to be using in our examples, and it transfers it to something called the s domain. Okay, and what I mean is if we have some function, let's say x equals t to the power of n, right? The Laplace looks like this. It's a curly L, and then inside the L, you put your function. So the Laplace transform of t to the n, okay, this takes something in the domain of t, right? N is just some constant. We're going to say it's greater than 1, and it's going to transform it into the s domain. So this is what we call capital F of s. Okay, so I don't know if you remember, but capital F typically stands for an antiderivative. So this is the antiderivative function involving s. Okay, you might be wondering, well, why does it have an antiderivative, right? We started with just t to the n. Are we going to have to take an integral of this to get capital F of s? What's going on here? Why is the s even here? So I'll show you right now what the actual process of transforming this function is. So let's take a classic example, the Laplace transform of e, the exponential to the power of lambda t. Okay, so this is a fairly basic function. Okay, lambda is just some constant, so it could be like e to the 2t, right? E to the 1t, e to the 5t, right? Lambda could also be negative, but I'm going to give you kind of the specifics on that after we solve this, okay? So actually, instead of e to the lambda t, let's just go f of t. Okay, so what the Laplace transform does is it takes a function f of t and it puts it into an integral. So the integral is from 0 to 100, so it's an improper integral, right? One of the bounds is 100, and it's the integral of e to the negative st f of t dt. Okay, so this integral, it might seem kind of out of hand, like unnecessary. What the heck does this mean? Why is the s there? Why is there an exponential? But you'll find that no matter what we plug in for f of t, it's going to be in the t domain, right? Because the variable's t. And when we solve this integral, we're going to get something as a function of s. Okay, so every single time we're going to transform it from the t domain to the s domain. Okay, so let's say we were taking the Laplace transform of e to the lambda t, like I just talked about. I'll write an equal sign here. So this is going to be the integral from 0 to 100 of e to the negative st times e to the lambda t dt. So our f of t, right, our function with respect to time is e to the lambda t, where lambda is some constant. Okay, so now we can kind of simplify this. Notice how these are both exponentials with base e, and they're multiplying. So that means we can add their exponents. And when we do that, right, and we factor out the t's, that's going to be from 0 to 100, the integral, right, of e. And let's factor out that negative. So e to the negative s minus lambda t dt. Okay, and what we can do now is do a u substitution. Okay, so let's say this entire exponent here is our u. That's typically what we do. If it's e to the power something, we just say u equals that something, so negative s minus lambda t, right? And that means that if u is negative s minus lambda t, then du, right, the derivative of u is going to be negative s minus lambda and then du. Or sorry, this would be dt, sorry, not du. So, actually, I'll move this over a bit. Okay. So, plugging all this in, right, if we know that our u is negative s minus lambda t, and our du is negative s minus lambda du, right, because that's just the derivative of this. S minus lambda is a constant, t is our variable, so the derivative is just the constant itself, right? And what we get is we're going to get the integral from 0 to infinity of e to the u, so that takes care of this. And then next we're going to go negative 1 over s minus lambda, right, du. So if we were to solve for dt, right, that would be 1 over negative s minus lambda. That's why we have it here, right? And then we have to multiply by du. So what I mean is dt would equal 1 over negative s, whoops. Man, gotta zoom in here. Negative s minus lambda du. So if we were to plug in dt here, that's exactly what we just did. Okay, so everything's in terms of u now. S and lambda are just constants. Okay, cool. So now we're going to try and simplify this as much as we can. I'm going to start from the left now. Negative 1 over s minus lambda, that's just a constant, like I said, right? This function, or this integrand, is in terms of u, right? U du. So we're going to factor out that negative 1 over s minus lambda. And then we're just going to rewrite the integral from 0 to 100 of e to the u du. Okay. And the integral of e to the u with respect to u is just e to the u. So this is going to be negative 1 over s minus lambda times e to the u, right? And this is going to be evaluated from infinity to 0, right? That's really what the integral is doing. Okay, so if we actually evaluate it, right, this is going to be, well, actually, before we evaluate it, we have to plug in what our u is. So it's going to be u is negative s minus lambda t. So 1 over s minus lambda e to the negative s minus lambda t, evaluated from infinity to 0. Okay, let's just kind of plug in infinity for t and 0 and see if we can get a real answer. Okay, so if we plug in infinity for t, this will be e, we're going to ignore this constant right here because it's just a constant, e to the negative s minus lambda times infinity. And you'll notice that no matter what s and lambda are, if it's negative times s minus lambda times infinity, we're going to assume for now s minus lambda is positive, so s is greater than lambda. Why is an equal sign there? So this is going to be e to the negative infinity, which is just 0. So this is going to be 0, e to the 0, sorry. To the negative infinity. Hold on. I'm actually going to write this out. 1 over s minus lambda times, okay, so if we write infinity for 0, this is going to be e to the negative s minus lambda infinity. So it's essentially e to the negative infinity. Okay, and then if we plug in t for 0, and I'm going to write, I can't forget my negatives here. This is going to be minus e to the, well, if we plug in 0 for t, it's just going to be e to the 0. So e to the negative infinity, remember, that's just 0 because this is 1 over e to the infinity. So this is going to go away super fast. and we're just going to get minus e to the 0. E to the 0 is just 1. So it's really just this times negative 1. The negatives now cancel, and we just get 1 over s minus lambda. Okay, so this is our capital F of s. So we successfully transformed the function f of t equals e to the lambda t. Right, we took the Laplace transform of it, and we got 1 over s minus lambda. Okay, I'm going to do a bunch of these examples. We're going to kind of build a table of different Laplace transforms we can use. But until we complete the table, it's not going to be 100% clear why we're doing it. Okay, so all I can tell you right now is it's going to help us when we're solving differential equations. It's going to make our lives a lot easier, but you just have to trust me right now, okay? I know it's kind of weird, like going from an exponential to like 1 over s minus lambda. That's like a constant in the case we started before, but then it's a function of s, so this is a rational expression, right? How are we even getting this? Well, just trust me on this, okay? So the conditions for what we just solved for here is s is greater than 0, okay? Actually, s is actually greater than or equal to 0, because if s is 0, this would be the Laplace transform. Oh no, sorry. S can't equal 0. So s has to be greater than 0, but lambda can equal 0. So I'll just say lambda is an element of the real numbers. Okay, and s also has to be greater than lambda. Okay, because like if we have lambda greater than s, this will be 1 over a negative number. Okay, and we don't want that. So that's kind of the conditions we need to work with there. I'll just rewrite this here. So s has to be greater than lambda. Okay, cool. And notice if we chose lambda to be 0, for example, we took the Laplace transform of e to the lambda t, so this would be e to the 0t. Okay, that's going to equal, well, e to the 0t, that's just 1, right? Because it's e to the 0, so it's the Laplace transform of 1. Well, that's kind of cool. Now we can figure out what the Laplace transform of 1 is using the kind of the formula we just found. So if lambda was 0, this will be 1 over s minus 0, which is just 1 over s. Okay, and we'll figure out how we get that equation in a separate video, but right now I just wanted to do one example of how we could transform a function in the t domain. Okay, actually I'm going to do one more with you, okay? I'm going to do 2 in this video. So let's do the Laplace transform of t to the n. And I'll just write up here, t is greater than 0. Or t, not t. Sorry, it's early in the morning here. N is greater than 0. Okay, and we're going to say that equals, right, with our improper integral of e to the negative st, t to the n dt, okay? So n, s, and t, as we know them right now, they're just constants. Okay, and what we're going to do with this integral right here is we're going to go integration by parts. Okay, the reason we didn't have to in the last one was because it was an exponential times an exponential, and we could just add their exponents. But for now, right, this is base e exponent, this is base t exponent. Okay, so the t's in the exponent, in this one the t's in the base. We can't really do anything with our exponent laws there. Okay, so we're going to say, u equals t to the n, right, because it's algebraic. So in the acronym I created before, it was LIATE, right? So E is exponentials and T is algebraic. That one's going to be your U there. That means that du, right? If we write it generally, it's going to be n times t to the n minus 1. So remember, we don't know what n is. We're just leaving it general. Okay, and then we need our dt there, of course. Okay, and then dv, that's just That's just other stuff, so e to the negative st dt. Okay, and then we have v is just the integral of that. So it's going to be negative 1 over s e to the negative st, right? Because if we did a u substitution here, we're going to end up just getting like 1 over the derivative of this times this exponential itself. Okay, so once we use that, right, integration by parts means, or it tells us this integral is equal to uv minus the integral of v du, right? Our u is t to the n, our v was negative 1 over s. How could I write this a bit simpler here? I'll just write it the way it is, negative 1 over s, e to the negative st, and then minus the integral of v, right? V was just negative 1 over s, e to the negative st, and then du was n, t to the n minus 1 dt. Okay, so it's getting a little confusing here. Let's just kind of simplify a bit. So I'll actually, yeah, I can't really move this over. I'll write down here just for a bit more room. How can we simplify this one here? So this is going to be, let's take out this negative here over here. So it's going to be negative t to the n. Okay, and then it's going to be 1 over s e to the negative st. And this is evaluated from 0 to infinity, just like the integral is. So I forgot to write my bounds just because I don't have a ton of room, but I'll squeeze them in here. So this integral is from 0 to positive infinity. Okay, so when we take integration by parts, we have to apply that 0 to infinity for both kind of parts of the integration by parts we get, both terms. Okay, and then when we simplify this right side here, we see that these are both negative, so we can call it plus. And remember, n and s are constants as we know them now. S won't be a constant once we solve this. It's going to be our new variable, but right now it is a constant. So we can pull it out and say it's times the integral from 0 to infinity. And what we're left with is e to the negative st, t to the n minus 1 dt. So we had 1 over s, we multiplied it by n, made these negatives positive because there's 2 of them, and what we were left with was just this t to the n minus 1, right, and just this e to the negative st. Okay, so now once we've done this, we have to plug in infinity and 0 and actually evaluate these limits here. Okay, we actually have to evaluate them, and what you'll notice too is this right here, this is the Laplace transform of t to the n minus 1. Okay, so that's kind of cool, right? Because we started with the Laplace transform of t to the n, and we have a bunch of junk in front, right? We have a bunch of junk in front, and then we're left with the Laplace transform of t to the n minus 1. So there must be some kind of formula that we can work out with this, but let's just see kind of where we go here. So if we evaluate this limit, this is just the limit as h approaches infinity of h to the n, right, minus the limit as h approaches 0, right, of t approaches 0 of t to the n here. So if we plug in infinity for t, right, that's our variable right now, we're going to get negative infinity to the n times 1 over s e to the negative s, I don't know, right, infinity here, minus, okay, right in brackets, if we plug in 0, it's going to be negative 0 to the n, 1 over s, e to the negative, I'll just write 0 because it's s times 0. Okay, so negative infinity to the n, that's going to be negative infinity, times 1 over s, that's a constant, e to the negative s infinity, that's going to be e to the negative infinity. Well, e to the negative infinity is 0, so this is like negative infinity times 0. And since this exponential overpowers this polynomial here, we are going to say that this limit equals 0. So this part is 0, and then it's minus negative 0 to the power of n, which is 0, times e to the negative 0, which is 1. So it's 0 times 1, which is just 0. So the whole thing becomes 0 on the left there. The entire thing just becomes 0. So we can just rewrite this. This essentially goes away. So we can just rewrite this integral as n over s times the integral from 0 to infinity of e to the negative st t to the n minus 1 dt. So when we do integration by parts, we kind of get rid of this junk in front when we evaluate the limits, and we realize that the Laplace transform of t to the n equals n over s, right, times the integral of the Laplace transform of t to the n minus 1, and I kind of mentioned that over here. Okay, so if we do this recursively, what we're going to notice is that if we take if we now take the Laplace transform of all this, right, we're just going to get, like before we had n, but then we got n minus 1. So if we did this again, it's going to be n times n minus 1, right, because that's like kind of our new exponent, and it's going to be over, before what we got was, it was over s. We're just going to get another s on the bottom if we did this again. And you can do this yourself, honestly. I'm not going to prove it, but if you just keep doing the Laplace transform of this, right? So if t to the n minus 1 was your new function, you would just kind of get what we're doing right now. So you get n times n minus 1 over s times s, and then you'd get the Laplace transform, right, of t to the n minus 2 now. So before it was n minus 1, now it's n minus 2, and you can just keep going, right, until you get to the Laplace transform of 1, right? Because eventually, like, if, say your n is 5, right, if, say, n equals 5, you would keep going until you got the Laplace transform of t to the n minus 5, and that's where you'd stop, right, because you'd get t to the power of 0, and once you got that, it would just be 1. So you'll notice there's a bit of a pattern here. This n times n minus 1, if we kept doing this, it would be n minus 2, n minus 3, and that's factorial, right? So the Laplace transform of t to the n is equal to n factorial over s to the n, right? Because however many times we take the Laplace transform, that's how many s's we have. So when we only did it once, we only had n over s. Then we did it again, we got n times n minus 1 over s times s, so this is s squared. It's s to the 2 because we did it twice. So it's s to the n times the Laplace transform of 1. Okay, well, we figured out above, remember in our first example, that the Laplace transform was 1 because when we plugged in 0 for e to the 0t, we got 1. We just used our formula that we created, right, and we found it was 1 over s. So this is really n factorial over s times n, or s to the n, times 1 over s. So I'll rewrite this here, equals n factorial over s to the n times 1 over s. So since these are both base s, we can use our exponent laws and say this is equal to n factorial over s to the n plus 1. Okay, because this is s to the first power. So what we do is we just add the exponents, and this is our general solution here. So if we have some function t to the n, we take the Laplace transform of it, we have a new function in terms of s, right? There's no t's there. And I said that before, I said you have to trust me, right? We're going to have a function in terms of t, we're going to take the Laplace transform of it, and then we're going to get a new function in terms of s, and it's just some constant. So we're going to do examples later, but remember our function was t to the n, so n would just be the exponent that you would put there, right? That's what n is, it's just a constant. Okay. So the only condition that we have for this is that s is greater than 0, but that's all that really matters, right? So if s is greater than 0, we've kind of met everything. We've met all the conditions there. So I did the first two examples with you there. I hope those made sense. In terms of like why they're useful, like I said, for differential equations, much easier to solve. But for now, you just have to trust me. So we're going to kind of build a table. We've already done t to the n of polynomial. We've done exponentials, right, e to the lambda t. And I'm going to show you some pretty cool properties of the Laplace transforms as well in the next, I'd say, 5 videos, okay? So thanks for tuning in, and I'll see you in my next one.